मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी।
Sixteenth lecture in the series of mechanics of metal forming. Friends, the last two lecture that we started with yield criteria, the concept of yielding and related yield criteria that has been possible. We started with the aim that let us develop the criteria, let us see the criteria that people have developed, and one can use it for modeling in metal forming of different processes. So, in this series, in particularly this lecture, previously we have already discussed the many issues like von Mises yield criteria and related issues. So, here we would be discussing the yield surface, and then we would see another yield criteria apart from von Mises and Tresca yield criteria, the Hill's criteria, and also we will see that these three criteria like your von Mises, Tresca and Hill's criteria, let us which one is the best on the basis of experimental verification. So, let us start with some very simple problem which previously we did for von Mises equation. We established the criteria that it is the flow function which will is the von Mises flow function and flow rules and all those things. So, let us see this problem number 1, where if you look at this matrix T, so here it represents a metal body in plastic steel under the action of following stress tensor, where the stress states are shown. So, it has 9 components, again one can see. So, the question is to find the yield strength of the material in tension as well as in shear according to the von Mises yield criteria, and let us assume that the values of the stresses that is given, it is in Newton per mm square. So, how would we start solving? So, the stress tensor is given here. So, if you recall back the previous equation, where so one can find out what we should find out. If you recall the von Mises equation, 6k square, that this value where k is the constant, we should find it out of the, and if you recall equation, what was the equation? So, sigma minus sigma 22 square plus sigma 22 minus sigma 22 minus sigma 33 square, and those 3. So, there was 4 terms in that, if you recall. So, if you compare this, we can find it out the value of yield strength in shear. Shear terms are sigma 11, sigma 22, sigma 33. So, like sigma 11 is 120, sigma 22 is minus 100, and sigma 33 is, and other components, shear components are here. So, we can start with like here, that is 120 minus minus 100, that is sigma 22 square plus sigma 22 minus sigma 33 square plus sigma 33 minus sigma 11 square plus 6 sigma 12 r xy plus square of that plus sigma 23 square plus sigma 31 square. So, if you add all these values from the this tensor, we get the value as 140.83 Newton per meter square, and therefore, the yield strength in tension, that is sigma of the material, as if you recall we established. So, it can be found at root 3 K, and that comes out to be 243.93 Newton mm square. So, this is what a very simple problem, and one can use this equation related to a given stress state. Now, let us go ahead with the yield surface. So, if you recall back the yield surface that we plotted the equation number probably figure number 8. Now, recall all those figures, figure number 8, 9 and 10. So, the Tresca criteria, which was written as sigma max minus sigma minimum, that is equal to sigma, and that is the 2K. So, when it is drawn in the principal stress space, it gives a solution. This can easily seen when it is the projection of the stress state is plotted on pi plane, and that we have seen. So, if you look at the figure 8 again, and that too the sector AOC, where sigma 3 lies between the value of principal stresses sigma 11 and sigma 22. The Tresca criteria, if you apply, this will give sigma 22 minus sigma 11, and which is equal to sigma. This criteria in the sector AOC will give the line which is parallel to sigma 33 axis, and at a distance x, if you look at the previous figure, so at a x is determined as sigma 22 minus sigma 11 under root 2. So, this equation 30, if you recall earlier the equation 53 as well. So, using the yield criteria, this particular equation gives x is equal to sigma by root 2, especially for sector AOC. So, from symmetry consideration, the complete yield surface can be drawn, and that gives a regular hexagon within the von Mises circle, which is previously shown in figure number 9. So, yielding is now represented by a point on the hexagon. From the figure 9, it is then clear that the minimum difference between the von Mises and Tresca criteria occur particularly at x is equal to 0, one can see from the figure number 9, and it is the and its value at theta is equal to 0 is 0.159, one can see. So, Tresca yield criteria in principle stress space is therefore a regular hexagonal cylinder, and which is within the von Mises circular cylinder, which is shown in 7 figure. So, but in case of plane stress also, the Tresca criteria gives a hexagon within the von Mises ellipse, which was previously shown in figure 10. So, Tresca criteria and von Mises criteria, so far we have seen it is quite regular, but the yield criteria that assume that the yielding starts when the sum of the two largest principal shear stresses. So, Hill proposed another criteria in his name as called as the Hill yield criteria. It is slightly different with the Tresca criteria, where it assumes that the yielding starts when the sum of the two largest principal shear stresses, that is tau max and tau minimum, reaches a critical value. Thus the criteria can be written as the function, that is the flow function f, that should be tau max plus tau minimum, and that should be equal to a constant. And under the situation when the sigma 22 lies between sigma 11 and sigma 33, the principal stresses, then sigma 11 when it 12 lies between sigma 13 and 23, and the yield criteria will give from this particular flow function, the Hill's flow function, and that would be simply sigma 13 plus sigma 12 is equal to half of sigma 11 minus sigma 33 plus half of sigma 11 minus sigma 22, and that if you simplify, it becomes sigma 11 minus half sigma 22 plus sigma 33, and it is a constant, equal to constant. So to this equation, that is which is converted from equation number 71, if it is used for simple tension, that is sigma 11 is equal to sigma and sigma 22 and sigma 33 are equal to 0, this will give a constant as sigma. Whereas if you use it for pure shear, in the case when sigma 11 is equal to minus sigma 33, and that becomes the shear stress of the material K, and sigma 12 is 0 in, and the constant in that case it becomes as 3 by 2 K, and therefore the 71 can be written as the flow function, particularly for shear case F becomes as sigma 11 minus half of sigma 22 plus sigma 33, and that is equal to sigma, which is equal to 3 by 2 K for the shear case. So the Hill's criteria can be expressed as sigma 11 minus 1 by 2 sigma 22 plus sigma 33 is equal to sigma, and therefore the other three counterpart can also be written. This equation number 73 set of three equations, it is that the Tresca yield criteria assumes that yielding occurs when the largest principal shear stress, that is tau max, attains a critical value and does not consider the effect of intermediate principal shear stress or any intermediate principal stress. So the Hill's criteria on the other hand considers the influence of intermediate principal stress. This point is to be very particularly noted. So if we use a flow function, the flow function which has been derived from plastic potential, that is strain increment. So the strain, any strain increment tensor can be which is equal to deva g sigma I j divided by deva sigma I j d lambda. If you recall, this is the plastic potential. So the associated flow rule can then be obtained when the sigma 22 lies between sigma 11 and sigma 33. So one can obtain that this flow rule, if you insert the flow rule here in the plastic potential concept, so it becomes deva f by deva sigma 11 is equal to 1 and deva f by sigma 22 is equal to minus half, and deva f by sigma deva sigma 33 is equal to half, and therefore d epsilon 11 it becomes equal to d lambda, d epsilon 22 becomes is equal to d epsilon 33, and that becomes simply minus d lambda by 2, and therefore d sigma 11 becomes minus twice d sigma 22, and that becomes minus twice d sigma 3 3. So this is how 1, 2 and 3 is associated as shown in equation number 76. Now we can again establish in terms of the generalized stress and generalized strain increment. So if you recall back, the incremental plastic work was calculated as dW, which was given as sigma 11 plus incremental strain 11 plus sigma 22 incremental strain 22 plus sigma 33 incremental strain 33, and that was given as the generalized stress multiplied by generalized strain increment. So previous equation number 76, if you utilize and we substitute, so this plastic incremental plastic work can be represented in as shown in equation number this particular equation 79, and that comes out to be equal to sigma 11 minus half of sigma 22 plus sigma 33. The generalized strain increment therefore can be obtained as d generalized strain is equal to d strain increment 1, and that is equal to d lambda. So if we see the yield surface, the Hill yield criteria, when it is plotted on a principal stress space, it represents a regular hexagonal cylinder which is outside the von Mises cylinder that we have already, now you can see here. When it is plotted on pi plane, it will therefore be a hexagon which is circumscribed by the von Mises yield locus as shown in figure 11. Here the Tresca yield criteria locus is represented by in figure number 11 by inner hexagon which inscribes the von Mises circle, while the Hill's yield criteria locus represents the outer hexagon circumscribed within the von Mises, as one can see here in on the pi plane, this one, and these 12 sector, all the 12 sector has been shown here, and therefore one can notice that this particular sector, that is AOB, BOC, COD, DOE etc., where the depending on the sector the stress, for an example, if you see here for the sector BOC, the sigma 22 lies between sigma 11 and sigma 33. Okay, so one can see the how it is drawn. So the according to the Hill's criteria, the hexagon is outside von Mises criteria, and Tresca criteria, it is the hexagon is inside the von Mises criteria. One can very clearly see here, and one can plot it, and because if you plot all the sector you get this particular and the position of the Hill's yield criteria on pi plane is shown here. So from the earlier derivation, if you recall the equations 53 probably and 54, where it was calculated as x to find out the location of the vertical line which comes out of the hexagon, it was calculated x as sigma 22 minus sigma 11 root 2, and y was also calculated as twice of sigma 33 minus sigma 11 plus sigma 22 by 2, the whole divided by under root 6, and therefore the Hill's criteria, whereas the Hill's criteria gives sigma 11 minus half of the sigma 22 plus sigma 33, and which is equal to sigma, and therefore for the Hill's criteria y comes out to be under root 2 by 3 sigma, and for the sector COD as shown previously in figure 8, one can see here it again for the plane stress condition. If you apply it for the plane stress condition, on the pi plane it looks like circle and the hexagonal, but in the plane stress condition, we earlier also we have seen it for von Mises and Tresca criteria, but here if you see in this figure number 12 on the plane stress condition, one can see very clearly that this hexagon is outside in the Hill's criteria. We are particularly dealing with isotropic material, as you know, for all the three criteria concerning here. So one can very clearly see for the sector say COB, BOA and correspondingly, and one can see the position here. So one if you look into if you see the symmetry consideration in all these 12 sectors, the yield locus on pi plane will be a hexagonal which is circumscribing the von Mises circle, and in case of plane stress the Hill's criteria gives a hexagon which is outside the von Mises ellipse as shown in 12 figure. So all the three criteria are popular, but let us see when we all the three are available, which one we should rely more. So there are experiments, lot of experiments has been carried out by many people. So let us see the experimental verification of these yield criteria. The most common and the simplest method of experimental investigation of the yield criteria is to use an approach in which thin walled tubes are subjected to combined stresses. So in 1926 around, Lode was perhaps the first one scientist to conduct experiment on steel, copper and nickel tubes under various combination of longitudinal tension and internal hydrostatic pressure. So these whatever experiment he carried out, it was recorded and it is shown in figure number 13 here. So he devised a very sensitive method of differentiating between the Tresca and von Mises yield criteria by determining the effect of the intermediate principal stress on yielding. So one can see here in 13, this is the cylinder which is thin cylinder and it is subjected to the load P, axial load, and it is subjected to pressure in the form of hydrostatic pressure as P. If you take an element here out of this and if we analyze, so the yield criteria on the basis of Tresca, one can have the sigma 11 minus sigma 33 by sigma which is equal to 1. The Lode introduced a parameter nu which we call it as the Lode's stress parameter to account for the effect of the intermediate stresses. So nu was defined as the ratio of the difference between the intermediate stress and the average of the largest and the smallest stress to half the difference between the largest and the smallest stress, and therefore the Lode stress parameter nu for the sector where the principal stress 2 lies between 1 and 3, it can be expressed as nu is equal to sigma 22 minus half of the 11 plus 33 and divided by half of 11 minus 33 as said, and therefore the new Loday's constant parameter nu is can be represented in this form, equation number 84. And when the sigma 33 lies between sigma 11 and sigma 22, the Loday's parameter can be written as nu is equal to this, which is shown in equation number 85. The von Mises yield criteria, if you recall, on pi plane, for the similar case when the sigma 33 lies between sigma 11 and sigma 22 and which was derived earlier in equation number 56, and we can find it out the theta, which was theta was tan inverse if you recall back. So if you substitute this middle portion, that is nu, so nu comes out to be this right hand side, and where the tan inverse this right hand side whole thing fits divided by root 3. So if you simplify this, it is written in equation number 86 as nu comes out to be root 3 tan theta. So let us use the cases. So first case, when theta is 0, one can see from the equation 86 that nu is 0, and this gives that the value of nu, which is in equation 85, it becomes 0, and therefore it gives that sigma 33 is equal to sigma 11 plus sigma 22 by 2. When the stresses are sigma 11, sigma 22, and as determined the sigma 33, which is equal to sigma 11 plus sigma 22 by 2, the average of the two, which has the pure shear derivatives. So one can see here that this particular sigma 11 minus sigma 11 plus sigma 22 by 2, then sigma 22 minus sigma 11 plus sigma by 2, and C 0, and the hydrostatic part of the stress, which is sigma 11 plus sigma 22 by 2, comes. Now the second case, when theta is 30, nu becomes 1, and this gives the left hand side is equal to 1, and therefore the theta sigma 33 becomes equal to sigma 22. And in that case, in this particular case, when sigma 33 becomes equal to sigma 22, the stress state for this particular becomes the case as sigma 11, sigma 22 and sigma 22 for the when the sigma 33 lies between the sigma 11 and sigma 22. This is equivalent to the uniaxial stress, therefore, which is sigma 11 minus sigma 22, together with the hydrostatic stress, which is sigma 22. But when theta is 30 and nu is minus 1, this gives the another value, which is equal to, as shown here, 2 sigma 33 minus sigma 22 minus sigma 11, and it is equal to minus sigma 22 plus sigma 1, and this gives sigma 33 is equal to sigma 11. Here the stress state are sigma 11, sigma 22 and sigma 11 is equivalent to a uniaxial stress state, which is sigma 22 minus sigma 11, together with the hydrostatic part, which is equal to sigma 11. Thus, by varying the value of nu from minus 1 to 1, or the value of theta from minus 30 to plus 30, all the combination of loading from uniaxial tension to pure shear to uniaxial compression can be considered, and in terms of the principal stresses. Therefore, the von Mises criteria is given by equation number 90 here, one can see. So that becomes sigma 11 minus sigma 22 square plus sigma 22 minus sigma 33 square plus sigma 33 minus sigma 11 square, which is equal to twice sigma square. So but from equation number 53 85, where the sigma 33 becomes sigma 11 plus sigma 222 plus nu sigma 22 minus sigma 11 by 2. So, if you substitute the value of sigma 33 from equation number 91 into equation 90, so this gives this relationship, which is as equation 92, and the Tresca yield criteria, therefore it is given as sigma 22 minus sigma 11 by sigma, which is equal to 1. The difference between the Tresca and von Mises yield criteria can now be determined by how much the right hand side of this particular equation differs from the unity, therefore. So, when we take the nu as -1 r plus 1, that is in the case of uniaxial tension or compression case, both von Mises and Tresca criteria, which is shown in equation 92 and 93, gives the value as shown in the right hand side of as, and it is equal to 1. So, if you see the experimental results, which was carried out by Lode, when it is plotted at here, the x axis, the values as -1, then -0.6, -2, 0, then 0.2, 0.6, and here, and on the other side this factor sigma 11 minus sigma 22 by sigma, it is plotted here. So, one can see that when nu is 0, one can see here for the steel and copper, all the points lies towards the von Mises criteria, one can see this curve, and Tresca criteria corresponds to where this value is 1. So, for nu is equal to 0, which represent the pure shear state, the Tresca criteria become sigma 22 minus sigma 11 by sigma, and this is equal to 1. While the von Mises criteria gives sigma 22 minus sigma 11 by sigma, which is equal to 2 by root 3, and this is 1.156. So, this is the place where the maximum deviation occurs between these two yield criteria, von Mises and Tresca. Another set of experiment was carried by Lode in 1926, where he conducted a series of experiments covering the value of nu from -1 to +1, r in the form of theta from -30 to +30, and he obtained lot of experimental results, and it is plotted in the next figure, which is 14. Here the data, if you see, favors the von Mises criteria, even though there is appreciable deviation. These deviations were actually partially attributed, which was mentioned that it was not there was a lack of isotropy in the test material. So, later Taylor and Quenin in 1931 conducted another set of experiment for the situation slightly different as the Lode, and Taylor and Quenin in 1931 carried out tests for the thin copper and steel tubes, which were almost isotropic, and it was under combined tension and torsion. Now, if you look this particular figure 15, this is the tube shown here, and you see here the axial loading P, and there is a torsion T. And now, if we out of this tube, if we take an element as shown, so this element is shown here in equation figure 16 from the tube, and then one can see that there are two stresses, sigma 1 xx and sigma yy are present and others are 0. So, if we cut from the tube this particular which is subjected to tensile stress sigma ZZ and shear stress as sigma XY, one can assume to be constant throughout the tube wall. The principal stress at a point of the tube wall therefore is equal to sigma 1 which is sigma xx by 2 plus under root sigma square xx by 4 plus sigma xy square. Similarly, the other counterpart part sigma 2 is sigma xx by 2 minus under root sigma square xx by 4 plus sigma xy square, and 3 is 0 since. So, if you look at the figure 17 here, which is the yield criteria and is various yield criteria is compared by the Taylor and Quenen experimental data, and if you see here the xx, and this is what is the shear part of that. So, one can see that the von Mises yield criteria falls in between and the hills is above the von Mises and Tresca is below. And when it is plotted for the mild steel, copper and aluminum, one can see the most of the point is scattered around von Mises yield criteria, and therefore, the von Mises yield criteria becomes here from equation 31 under. So, therefore, it can be written the von Mises criteria as sigma xx by sigma whole square plus thrice sigma xy by sigma square, which is equal to 1. And this is what is again if the values which is obtained here in figure 17, if it is again plotted it on sigma 11 and sigma 22 plane, one gets the experimental result like here. So, the Tresca it gives the diagonal. So, the Tresca gives the value of diagonal which is a straight line, and von Mises is between Tresca and Hill's criteria. Also, the point is to be noted that the most of the point is closer to the Hill's criteria. So, again this shows that there is a Hill von Mises criteria is quite better. It is because the points are very close to the von Mises criteria. If you substitute this value from equation number 95, that is the von Mises yield criteria, if you substitute here, then the Tresca criteria gives the same thing as sigma xx by sigma square plus 4 of the sigma xy by square which is equal to 1. And similarly, if you substitute according to the Hill's criteria, that gives where that has been sigma 11 minus half of the sigma 22 plus sigma 33, which is equal to sigma. This gives as sigma xx by 4 plus 3 by 2 sigma xs square by 4 plus sigma xy square under root this, and it is equal to sigma. So, if you look the equation 95 to 97, this gives sigma xy which is equal to sigma by root 3 sigma then sigma by 2 and 2 sigma by 3 for the cases when it is pure shear. For comparison, if you compare these criteria and as shown in figure 17, this shows that the experimental data in general fits towards von Mises criteria. It is better than the two criteria. For the case of mild steel, say, the data however fits closely towards the Hill criteria. So, if you replot it on say sigma 11 and sigma 22 plane as in equation figure 18, that also indicates that the data, it is very much favorable to von Mises criteria, and in both the figure 18 and earlier, it is seen that the most of the data point lies between the Tresca and Hill's criteria. So this guides, this whole set of experimental guides, data guides, that the most of the cases, practical cases for the forming, analysis, modeling, it has been observed the von Mises criteria gives a better one, and therefore I suggest that von Mises should be used for most of the problem. So with this, the yield criteria, which would be quite useful subsequently onward for the other part of the analysis. I thank you all for your patience, and I will request that you give your feedback so that we can improve for the future. Again, to remind you that the problems, objective problems are also given on the website, and you can try yourself understanding of these lectures. So thank you all, thank you once again.